Hi. So we have been talking about how to set up basic simulations, just looking at orbital mechanics. At this stage, we want to make the spacecraft actually do something actively, such as an attitude maneuver. So here, let's look over the basic scenario that you would have. If you look at the orbital, we went through a lot of these earlier. Inertial 3D pointing is kind of the first hello world attitude dynamics, attitude control scenario that we've got right now. So we're going to click there and let's look at this actual simulation outline. We already know how to make a process, a task, add a spacecraft, add gravity like Earth. This is what we had earlier. Now we'll have a few new modules such as external force torque and SimpleNAV. External force torque allows me to just add a control torque or control force to a spacecraft. And we'll talk about that in more detail. SimpleNAV, it's essentially something that mimics some device that provides you an estimated attitude or position or both out of a system. So this could be like a Star Trek you're mimicking, and you can add noise. And we'll talk about this in more detail. So right now we're not actually going to be adding much noise. We'll just feed it through and it puts out flight software messages that can connect to the different modules. Then in yellow, we've got some flight software modules we're going to be using. One of them is called inertial 3D. And the other one is attitude tracking. Inertial 3D gives us an attitude reference. Where do we want to be pointing? And here it's just a static point at this part of the sky. Attitude tracking error takes the information from where are we actually pointing, at least the estimated one, and where should we be pointing, and it computes your attitude error states in both, the MRP attitude error, but also the angular velocity attitude error, and so forth. So it computes all of that, which is then used in a feedback control law. And then we're just getting an external control torque that gets attached to this external force torque module. This is how we're going to close the loop, and it should do maneuvers. So there's a variety of modules that we will have to look up, and we'll talk about them as we go through the Python script. They're also linked here, so you can click on them, read more about them. They have documentation, and that's always a good way to go through that. When we run it, you should see, things like the attitude errors. This is in modified Rodriguez parameters. They're kind of converging to 0. 0 is good. That means we've achieved our desired outcome. Our control torques also go to rest. In one case, they go to non-rest because we can actually also model external torques as an unmodeled torque or external torque where we feed forward on it. And you will see cases in the code where it says, if we use external torque, then do this, right? There's also integral gain. You can see that's a flag for the simulation script. So we can turn it on and off, and you'll see that in the code. If, then do this, otherwise don't do it. Unmodeled torques, that means that external torque is not included or is, and then use known, this is in the control side. Show plots is the same. Use C message. Yeah, we'll talk about also connecting variety of messages, and also I want to show you here how we can redirect a flight software module to write to not its own output message, but to a standalone externally configured output message and connecting it. So simple simulation, but there's quite a bit of beef to this already, some complexity, subtle variations, and if you run the different scripts, you would see these different outcomes. So let's go ahead and jump into, this is now inside the examples folder. We're looking at scenario attitude feedback. There's a whole series of different attitude feedback ones that uses thrusters, ones that uses multiple threads, no Earth, that means you're just flying in deep space, one that uses reaction wheels or reaction wheels with power actually, tracking and so forth. So there's a variety. We're doing the first one. So if you look at the top, that's the usual RST documentation. You can just ignore that. That's what gives you the web page information. For importing, I'll open up this too. We import some standard Python utilities. From utilities, Basilisk, we import simulation base class, unit test support, macros, orbital motion, very similar to what we did with the orbit scripts. Then from the simulation side, we need spacecraft, external force torque, SimpleNAV, and this is sim include grav body. This is our helper class. This is the factory class for creating gravity bodies that we've discussed before. But now we have flight software. So from Basilisk.flight software, we're going to include MRP feedback, inertial 3D, and our attitude tracking error. So those are modules. These will be C modules, where everything before has been C++ modules. So if you remember your basics of Basilisk, creating a C module in Basilisk and a C++ module in Basilisk is almost the same, but there are some subtle differences that we have to account for. So here we'll be using it. Then we include messaging, as we always do, with support, so we can actually, if you want to, save it off to a binary file and play it back in Wizard. And this line is done because we're going to be talking about creating C-wrapped standalone messages. By default so far, if we just use the messaging system to create a standalone message in Python and then connect things to it, it was actually always a C++ message object. Here, if we want to create a C-wrapped message, which is actually just a structure that contains message structures, message header structures, so the payload structure, the header structure, all that stuff. So for C messages, we can't do C++. We're going to show this, how to do it. We don't typically have to do this, but if you make more complicated simulation scenarios, you might run into this. So this is a place where we're going to show how to do that. Okay, now getting to the simulations, as we discussed, use unmodeled torques. That's one of the 4 flags. So that means in the control law, this means in the dynamics, we're going to turn on an external torque. And I'll show you how we can easily set that up with one module and then, see what happens. There will be this unmodeled torque. Your feedback control won't quite converge. You get Lagrange stability, boundedness. So that's the kind of thing. If you want to turn integral gain on, this is a way to compensate for unmodeled torques. Or if you want to feed forward on the torques, that's what this flag does. And then use C messages, you will see this kind of creates the standalone stuff that we'll be talking about. Okay, now this simulation, very similar to the orbit simulation we had. It's a single process, it's a single task. So we create our Basilisk framework. That's the simulation base class instance. We create a process, and then we create a task and add the task to the process. And we're running here at 10 Hertz. So our update cycle now is 0.1 seconds. This way, for attitude dynamics, this is good. So we can maneuver very smoothly within a few minutes. Simulation time up here, we're setting it to 10 minutes. So, but again, we're running at a much higher frequency than we did before. So that's pretty basic stuff. Now, going through the next. Spacecraft, nothing too much new here. We create the spacecraft object, add the model tag, we set the inertia, we're setting a mass. Don't strictly have to do it. The mass of the hub is typically initialized to 1 kilogram, and nothing in here actually depends on mass. If we had thrusters, for example, they put forces out, and so the net acceleration depends on, is it a small craft or a big craft? Then it would matter. Here, just the torques. We include it, didn't have to. Same thing here. We're zeroing out this, where's the center of mass of the body hub relative to the point B. We're making it all 0. That means the point B will be the center of mass of this single rigid body that we're modeling. So same as what you've seen before. We add the spacecraft to the task. So this would be the first thing that gets executed. Then we have our gravity body. We're creating an instance of the factory class, creating Earth. If you look down here, making it central body. What does that do? You should remember this now. If you say central body is equal to true, that means later on when you set the position and velocities, states of the spacecraft, the initial states of the spacecraft, those will actually be set relative to this body. As we only have Earth, Earth is the origin. So if you didn't set this, you get the same results because everything's around. By default, you're setting your initial position velocity relative to the origin of your inertial frame you've set up. So somewhat redundant, but it's really a good habit to write this and say it explicitly. Yes, Earth is my central body. I'm saving off mu just for plotting. And as before, we attach all the grav bodies to the spacecraft. Now we get into some new modules. This one here, external force torque. It's a module that allows you to just specify in a variety of ways an external force or an external torque acting on the body. So if you just want to mimic magically thrusters will be firing and generating 1 Newton of thrust in some direction, you could specify that this way without having to model the thrusters. But it's also useful if you just want to mimic some disturbance. If you're saying, look, I'm flying in a certain attitude and there'll be some disturbance torques acting on it, and this will generate 10 millinewton meters of torque, you can just specify a disturbance torque instead of having to model all the disturbances in high detail. This is also very useful for robustness checking and control development. So let's use this as an example to figure out how can we get more information about this module. I'm going to copy the name, go back to the website, and if I just type in here, external force torque, I look for the module, colon, and voila, here's the description. You can see there are 3 input messages that you can connect. So if I have a commanded torque, this is one we'll actually use in this example. This is our control torque that will try to stabilize our attitude in a particular direction. So then you would connect that one. If you had a commanded force, there's 2 options, one in the body frame and one in the inertial. If you're doing, for example, solar radiation pressure, it's probably easier to write that one, the inertial frame, and you can specify that one. If you have somehow thrusters acting or just saying, look, at some point there's outgassing, and regardless of the attitude, the outgassing is always in the left direction, in the Y direction, for example, you would connect this message. So what happens if you connect both messages? Well, these forces are superimposed. So you actually could connect a body fixed force and an inertial force all at the same time in one module, which is kind of slick, but just be aware, these are additive. So if you compute a force and add it in both ways, you're doubling that force, and you may not want to be doing that. So be aware of that. So we can connect forces and torques through messages into this module. If you look at the documentation, and this is an older module, this one has a documentation still in a PDF format. If you scroll through this, at some point, the user guide will talk about there's actually internal parameters you can set as well. These are visible to the Python layer. So there's an external torque about point B in the B frame, an external force in the N frame, external force in the B frame components. So these are the same 3 things that we do with input messages. We can also set via these parameters from Python. So when the module runs, these don't get updated unless you stop the simulation and then from Python change those values. But they are handy, for example, if you just want to model a constant external torque, you don't have to, create a message, connect it, have a separate module that connects a constant one versus one that does the feedback. So here, in this simulation, we're going to use this and to model a constant external torque disturbance. And the same module will connect this input message with the feedback control. So we get 2 torques acting on it, an unmodeled external disturbance and the active control torque all in one. So in fact, you have 3 input messages and 3 variables you can set. So there's 6 ways that you can affect forces and torques with this one module. So it's very flexible. It's one we use a lot, actually, for a lot of different simulations. Anyway, so this showed you a little bit. If you just want to search, find the name, search like that, this is a very convenient way to find more information. So this is a C++ module. So we just create an instance, add the model tag, and then these are the simulation flags. If we're using unmodeled torques, it simply sets this internal variable to this 3x1 matrix. It's a body frame matrix of that external torque vector. And that's it. Otherwise, this would be all initialized to 0. If a message is not connected, all the states are just initialized to 0 and don't get used. So that's cool. So here we can add that. Now we haven't added subscribe to our control torque yet. That won't happen until we actually computed control torque. So you will see this subscribing to a little bit later. This is an external force torque is an effector that affects dynamics. So here we still add it to the update cycle, because in the update cycle, at whatever rates, in the task that this get executed, it reads those input messages. So if you want this to be running at 10 Hertz, you better connect it to a task or add it to a task that's 10 Hertz. If you want to run this at 1 Hertz, you better put it to a task that is 1 Hertz. So you do want to add it, to a task, otherwise it never will run that update cycle. But at the same time, this external force torque needs to affect the dynamics of the spacecraft. That's where this extra line comes in. We haven't seen this before with our earlier tests. So the external force torque is the simplest one. Other ones would be, for example, reaction wheels or fuel sloshing or thrusters firing. Those are all effectors that affect, there's coupled multi-body dynamics that has to be solved especially if we get into hinged, single hinged, double hinged panels. So there's a command within the spacecraft class that has add dynamic effectors. There's two types of effectors, dynamic effectors and state effectors. The difference is dynamic effectors only affect, your differential equations of motion, but they don't have differential equations of motion themselves. So think of like solar radiation pressure. You just need to know what is the attitude from the spacecraft, and then you can compute everything you need to know. What's the position, what's the attitude? Same thing with atmospheric drag, or here, external force and torque. I just need their fixed values or specified through a message. They don't have internal equations, versus reaction wheels would have internal equations that would have to get solved. So then you apply motor torque, and given the spacecraft states, there's a couple differential equations that have to get solved. So more magic under the hood. This one is a dynamic effector, and so all we do is spacecraft object.add dynamic effector, and we add this. If you don't add this line, what you would find is when you run your simulation, all of a sudden, the feedback control is running, it's setting the torque, you can record the torque message and going, well, bloody hell, why is this not working, right? Well, you never added the effector to the spacecraft. So when it solves its equations, it sums up all the torques and forces that affect its motion. And this one simply is not included. So don't forget that line. That's an important one. It's an effector. Next new module, SimpleNAV. This is the one that simply has, it's a crude, it's not mimicking a particular device. It's just taking your true spacecraft position, velocity, attitude, angular rates, and then you can add corruptions. So you can add noise, you can add some random walk behavior and all this kind of things that you might see. So it's mimicking what will come out of a statistical estimation filter, like a Comet filter or something. So think of the star tracker that's already processing a signal and giving you a nicely processed attitude measure, but you can add noise and some corruptions if you want to. If you just create it like we're doing here, we're adding a model tag and adding it to the update list. We're not configuring anything else. That means we're using it in a feed-through mode. So by default, no corruptions will be added. If you want to add corruptions, go read up. There's other examples. You can read the module, there's big documentation, and you will find some sample scripts that add corruptions too. But here we're doing corruption-free. But this is what converts true states into flight software states that we can then tag and connect to our flight software modules. Next, we're going to start to create the flight software specific algorithms. So here, the first one is inertial 3D. And this is a C module, not a C++. So creating it looks slightly different. SimpleNAV was a C++ module. It's a class. We just make an instance of a class and have a handler in Python that we connect to it. This one here, we have to create the payload, which is basically the structure that contains all the data. This is like class variables you would have in a C++ class. We do that separately, and in the config, this is where we then specify, what's the gain, what's this state, what's this vector in this module. But to run it, run updates, resets, all of that, we have to wrap this, and essentially it makes a C++ copy that contains all these algorithms. So there's a lot of under the hood magic that happens here. But this is how we can run modules with C code, not C++ code. So we're actually recreating some of the features you would have in C++ in C. So the wrapped version, this is how we saw this earlier, the basic tutorials, how to make a C module versus a C++. We have to give it the content. So we give it the handle to that payload. We add the model tag to the wrapped version. The wrapped version is really what knows update, reset, all of that thing, self-init. And then we add it to a task. And here we do need to give it both the wrapped version and the content that stores it. So it needs to keep track of all of that. So just like what we saw in basic tutorials, we're now just doing a C versus a C++ module. Now, inertial 3D, what does it do? Its sole job is to put a reference output message out. And here it's going to be a constant inertial reference. So you can specify a desired frame R relative to inertial frame N, so sigma Rn, and there's an R0 because you can actually cascade reference chains later on if you want to. We'll talk about that in a separate one. But it's the reference frame relative to inertial, and then specifying that one here just to point at 0, 0, 0. So it's supposed to be identical. This is in terms of an MRP. Everything in Attitude is done in MRPs and Basilisk. So, and that's it. The angular rates and accelerations of the reference frame are 0 because here this is supposed to be a inertially fixed attitude pointing problem. So think of the Hubble pointing at some star somewhere. You would specify this is how you're supposed to look at that star. And then the control will drive towards that. So good. So now we've created a way to generate our reference attitude message. The next step is we need to compute the tracking error, and that's done through an attitude tracking error module. It's a C module, so there's this multi-step of making the content, making the wrapper, and then adding that one there. There's nothing else to configure in this one. There are a few options, and you can go read it at the documentation of this one. Here, we're basically not setting anything else, so this will give me an attitude error where it'll drive, in the end, the body frame to the reference frame and make them equal. If you needed the reference frame to be matched not with the body frame, but maybe with some cousin of the body frame, you know, instead of having a one axis look forward to the spacecraft, it looks to the right because that's where the docking port is or something. You can put in a correction and it will derive your reference to the corrected body frame, body fixed frame. We're not doing that here. So we're just configuring it, and then by default, it computes the error between B and R. That's all it does. But it does it in a very general way, which is actually nice. Now, the last one we need is the feedback. So we're using MRP feedback. This is a classic control that's in the textbook from the Schaub and Jenkins, used in many, many places. So it's just, it's a nonlinear feedback controller. It needs to know the inertia of the spacecraft that is in there. And there are options to use reaction wheels, but we're not modeling those here. So you won't see any particular code regarding reaction wheels. So by default, it just doesn't use reaction wheels information. So we're good. So again, it's a C module. So we got a few extra steps to set it up, get the wrapper, add it to the thing. And now I always have the stiffness K for the feedback control. If the simulation is using integral feedback, it sets it. Otherwise, it makes it -1. So in this module, by default, as soon as you create this one here, this is important to know because Swig, when it makes structures, it creates a copy of a structure, but it also nulls everything. So everything gets zeroed out. So there's no way to have, for example, the integral gain by default be -1. It's going to be 0. It checks in the code, though. If it is negative, it simply doesn't include integral feedback. So I'm setting it explicitly to -1 here to make sure that it doesn't use that. So just be aware, when you create structures in Python, this whole thing is using Swig. Swig will null everything out. So I'm always going to get a zeroed out version of this structure. And I want KI to be -1, not 0, if I don't want to use at all any integral feedback. P, it's my rate feedback gain. So that always set that one like K. So now I have proportional, derivative, and integral if desired. There's an integral limit you can set. You can read up in the modules. I'm setting it. It only gets used if the KI is not negative. And if we have a use known torque, that means in our feedback control, if we know what the external torque is, or we have an estimate on, we can feed forward compensate for that. And so if that is set, then this is the variable in the module, known torque about point B in B frame. That's how you would read this. And it sets it. So you can see already with the different simulation flags, this is where we're configuring our feedback control module in all its knobs. Let's see, we're missing one message. We will need a message that contains the vehicle configuration data. That means primarily for attitude control, we need to know what is the inertia matrix of this vehicle. And so there's different ways to create that. When we make standalone messages, we've seen this before, you basically go to messaging, you got your message name, vehicle config message, and then you add payload. This will create just the structure part of the message, just the content. So it makes a copy of that structure, and it will contain a variable called I, which is inertia of the spacecraft, PNT about point B underscore B. That means it's expressed in B frame components. So that inertia tensor is converted into a 3x3 matrix in B frame components. And we're setting it equal to I. I, if you notice, that was up here. The same thing, so for the spacecraft inertia, we set that to be our inertia tensor. And now for the flight software, we're using the exact same one. If you needed the inertia of the flight software to be slightly different because you want to model unknown parts, you think it's 100 kilograms meters squared, but actually it's 98 kilograms squared, you could modify what flight software uses versus what the simulation uses for the dynamics. So that's a way to test robustness of the system. So that just creates the content. We still need to make a message object. And I'm going to do this two ways. I'm going to jump ahead of the code. Well, if not, use cmessage. So by default, if we just create a message in the system, and there we just use vehicle config message, the name without payload, and that makes the C++ message object, and you get an instance of that. And that was it. And then we jump below, you do that message object dot write, and you give it the content. You put that content into that message object. And now config data message is a standalone message object that we can subscribe to from other modules. In fact, MRP feedback will have to subscribe to this module. So that's kind of the default way we typically do it. I'm going to show you here some other ways. We included the cmessage Python interface. It is possible, this line will make a C++ message object. There are times where we actually want to have a C-wrapped message, which in Basilisk is essentially a superstructure. It's a C structure that contains the payload structure and the header structure inside it, and some other little things that we need. So it's a way that in C, we can create these smart message objects, but they're the structures versus being full classes as they are in C++. Why would we want to do that? Well, if you have a C module that is writing to an output message, that's not its own output message, but it needs to write into another one's output, like a standalone message object. In C code, I'm using C methods to write to that message because that's all C knows. C doesn't know C++. And so to write to a standalone message, I need that message also to be a C-wrapped message structure, not a C++ message object. So otherwise, I cannot write to a C++ from C code. I cannot write to a C++ thing. Subscribing, we mentioned C, C++, C++ back to C, and so forth. It doesn't matter. Magic happens under the hood with Python that checks the connections and uses the right methods and calls to connect these things and read the content when you're subscribing. But when you're writing, you do need to be aware. So subscribing, not a problem, but writing is a problem. So how do we do that? Instead of doing message vehicle config thing, I have to call the cmessage py. That's what we loaded up in Python, that package. And then you have, again, the message name, vehicle config message, and we have _c with brackets. That will create, this is the one-line version. This will create in Python a copy of that message structure. And then we call a method on that called .init, and we give it the content. And that would work. Or if you want to do it in two steps, like what we're doing here, we create the message object, and then we wrote to it. You could also do this, and you just call init. Why is it important on the message to call init? Well, these messages, besides containing, the structure for the payload, the structure for the header contains information like when was it written, has it ever been written, who wrote me last, and so forth. There's also pointers to them. This is how we can redirect. So in the initialization process and the C structure, I have to make sure that the pointers point to my message's payload. The payload pointer points to the payload structure. The header pointer points to the header structure. That only happens after the initialization process. In C++, we have constructors, which is nice. So when you create the instance, it's automatically calling that constructor. And in that constructor, it makes those default connections that by default, the pointers for the message will point to its own payload and headers. We're not redirecting. I'll show you that below. Anyway, so a lot of content. I'm just doing this in case you have to write to external ones. Most of you, when you're just writing a simulation, will just create a C++ object put that data in there, and then you're done. And then later on, you subscribe to this message if something needs the spacecraft inertia. and you're done. This is a lot of chatting about how to do this with a C-wrapped message. So it's a subtle difference, but I have to discuss it somewhere. Okay, so this is a lot of discussion on how to make a standalone message in C++, and if you have to, in C, and have ways to write to that data. We're done making objects. This one's a standalone message. I don't have to add it to a task. It's just going to reside in the Basilisk simulation environment, and I can connect to it. Next thing up is making these subscriptions. So you can see the spacecraft, the navigation object, it has an input message called SC spacecraft state in message, and it's going to subscribe to the spacecraft object's spacecraft state out message. Kind of makes sense. This is how we get the truth in. And then SNAV objects here won't corrupt it because we didn't set up corruptions, but its output message will be subscribed to in attitude error configurations. So that's essentially this part. So the attitude error, the attitude out goes in here. And we also need to subscribe to inertial 3D to get the other one. So attitude error, the attitude reference in message subscribes to the output message of inertial 3D module. So now we've made those connections. The MRP feedback, it has two required input connections. One is the guidance. This is, it needs attitude B relative to R and the rate errors for B relative to R, all of that stuff. That is the output of the attitude tracking error. It computes everything that the guidance needs. So I just subscribe to that. But the MRP feedback also needs to know what is the inertia of the spacecraft. So I am going to subscribe to the config data message. This is the standalone message we created in Python that contains the inertia of the spacecraft. And then we're good. Now, let's see. Let's not use C first. So if we're going to use C++ stuff the standard way, I still have to connect the output of the MRP feedback. It computes a control torque, apply 1, 2, 3 Newton meters about the 1, 2, 3 axes, apply that at this instant. And it's done through an output message. This way it gets updated every cycle. And the external force torque object should read this as an input message and then update its force and torques every update cycle. So the external force torque, there's a commanded torque in message, and we can subscribe to the MRP feedback commanded torque out message, and this is what closes that loop. So if you go look at the simulation diagram, that's this dashed line. That's what we've just created, and that would do it. Here, if we're using C message, we talked about you don't have to write, by default, a module will write, it will contain a message object for every output type. And you will write to those message objects by default, but you don't have to. You can also write to another message object. That could be another object for another module, or just in this case, it's going to be a standalone version, but it has to be the same type. So when writing, you have to make sure that if this is code that's writing to a C wrapped message, it better be a C wrapped message object, not a C++. So if we have a C message, I'm going to show you here, we're going to create a standalone message, and we're going to redirect the MRP feedback to write to this standalone message instead of ourselves. Why? Just demonstrating that we can do that. Again, normally you probably just would do this unless there's a good reason to not do that. And if you do more complicated flight modes, then there might be good reasons. And we'll see that when we discuss BSK sims, like more complex flight mode simulations. But for now, we're just showing how we can do it. So as before, I need a commanded torque body message _C. This creates that message object. And I need to now direct, so I need to do, this is the add author command. So I need to direct the MRP feedback output message. Essentially, it has those pointers we talked about, right? There's a pointer to the payload I have to write, and there's a pointer to the header I need to write to. And I'm going to redirect those pointers to not point to the output message of this module, but to the standalone message that I just now created up here. And the way we do that is use methods that are contained in the C message py part. This is doing it to a C module. Later on, we can show you also how to do this. In the documentation, you will find discussions on how to do this with C++. It's a little bit simpler there. But you do have the message name, commanded torque body message _C _ add author. And then the first argument is, this is the module, that's your MRP feedback module. This is the output message. And when this module writes to this output message, the pointers won't point to its own payloads, but to this separate one, and that's specified here. So that makes that redirecting of the pointers. And that's good. And now the external force torque objects, the commanded in one, that connection we had down here where we just said subscribe, external force torque input, subscribe to the MRP feedback output. We actually are saying that external force commanded torque in, subscribe to, but not the MRP feedback's output message, but rather this standalone message object that we created. And it's a C-wrapped message object in Python. So you can see here, we'll be writing to a standalone message, and then that message is connected. And if you throw this flag on, it should still run. There should be no difference in code. It's just done in a slightly different way. Anyway, you can see a lot more tutorials on how and why do we do this. The rest of the script gets pretty straightforward. We're setting up how many data, roughly how many numbers we want to have. I compute my corresponding sampling time and setting up my recorders. So depending on if I'm using the standalone C message, I'm actually recording that standalone message, not the module's output. If I'm not using a standalone C message, then I need to record the output of the MRP feedback module. So be careful here. If you just record the output of a module, but you redirected that module output message to write to something else, the module content will just be 0 all the time. So when you record, you have to go to the right one. The rest of it is pretty straightforward. Now, classic stuff, we set up our initial position, velocity. We're actually also giving it an attitude rate. Before, we always gave it position velocity. So with MRPs, we could give it a 0.1, 0.2, minus 0.3. And I'm giving it initial angular velocity in the body frame. So these are in radians per second. So it actually has a slight tumble, and it's not pointing where it's supposed to. It's supposed to point at 0, 0, 0. And so if the feedback control will have to do something. Then we initialize it, we run it, we set it to run for 10 minutes. I pull the data and I can log and plot. So that stuff you guys are now masters at. If you want to change the script, what it does, you can change the flags down here. But right now, I'm just going to run this in the default settings. So I'm going to run that here. Actually, that's curious. You can see what I am running. It didn't adjust the background. That's curious. Interesting. This is my inertial position. It's in orbit, so I can still log orbits. It's not doing what it was doing. But if I'm looking at the rate tracking error, this is omega b relative to r. They're non-zero, and it's supposed to go to rest. So it does go to 0, which is good. The control torques do converge to 0, and the attitudes, as you'd expect, you want your actual attitude b relative to r to drive towards 0. And this would stabilize the spacecraft and bring it smoothly to rest at the desired heading that we're doing. Okay. That was attitude feedback, our first flight software modules. What did we cover? SimpleNAV. This is often the interface from the dynamics into flight software to get attitude and position states. We have external force torque. That's just a way that we have, it's an effector, the simplest effector where we can just specify apply this torque, apply this force, or if we want to add constant biases in there, if we want to just check robustness. And we talked about 3 flight software modules that we created, we connected, and created a closed loop simulation in here.